This video is about chapter 6 of our lecture on linear system theory, and it's about matrices as linear maps. In chapter 2, we have already characterized matrices as linear maps between the finite dimensional vector spaces R2 and R2, or more generally Rn and Rm. Now this concept will be extended by generalizing linear maps to abstract vector spaces, looking deeper into the fundamental properties of matrices as linear maps, and also looking a little deeper at linear maps on infinite dimensional vector spaces. Recall that in definition 223, we have already defined that by a map we mean a function between two vector spaces, and in definition 224 we have already defined a linear map for the complex vector spaces Cm and Cn. Now, with the concepts from chapter 4 and chapter 5, we restate this definition in terms of abstract vector spaces, which we call V and W. Then a linear map is defined as a function from V to W, such that for all vectors x1 and x2 in V and all scalars alpha in the field, the following two properties hold. First, additivity. So the linear map of the sum of x1 and x2 equals to the linear map of x1 plus the linear map of x2. And second, homogeneity. So the linear map of a scalar multiple of x1 equals to the scalar multiple of the linear map of x1. Two remarks about this definition. Matrices represent an important class of linear maps. It's not the only class of linear maps, as we shall see in just a moment, but of course they play a central role in linear algebra. And it's very important to think of matrices as linear maps. So you should not think of matrices as just a collection of numbers that are arranged in a rectangular order, but it's way more important to think of them as linear maps. So more specifically, if you have a matrix in Cm by n, then you have a linear map defined that maps from the vector space Cn into Cm, which is just given by a matrix vector multiplication Ax. And obviously this satisfies the axioms of definition 6.1, because clearly the additivity property is satisfied by this linear operator, which you can see by multiplying the matrix A with the sum of two vectors x1 plus x2, which is obviously equal to ax1 plus ax2. So it's the sum of the linear operators. And similarly, we can immediately see the homogeneity property by just multiplying the matrix A with a scaled vector alpha x1, which by matrix vector multiplication is obviously equal to alpha times ax1, so alpha times the linear operator of x1. Therefore, in the following, we will not make any difference between an m by n matrix A and its corresponding linear map from the vector space Cn to Cm. So the two things are considered as one and the same. Now that we've covered matrices as an important class of linear maps, let's look at some further examples of important classes of maps, where some of them are linear and some of them are not linear. In the first example, the map is called by the capital letter N, and it's defined based on an m by n matrix A and an m-dimensional vector B, and the map is defined for an arbitrary vector in the domain Cn by n of x equals to ax plus b. Now the question is n a linear map? On first sight, n looks innocent and linear, but if we go ahead and check the properties of definition 6.1, we find that n is actually not a linear map. Therefore, a map like this is actually called an affine map. To see that n is not a linear map, we can just check the additivity property. First, we calculate n of x1 plus x2, which by the definition of n as ax plus b leads to ax1 plus ax2 plus b. And second, we calculate n of x1 plus n of x2, which by the definition of n as ax plus b leads to ax1 plus ax2 plus 2b. So we observe that these two are actually not equal unless the vector b equals to 0. As a second example, we consider the so-called left shift operator that we denote by sigma n, where n is a natural number, and the left shift operator maps from the space of complex sequences, which we denote like this, into the set of complex sequences, and it's defined as follows. If we have a complex sequence from k equal 1 to infinity, and we map it by the left shift operator, we get another complex sequence, which now starts with the n plus first element of the original sequence. It's actually not a very complicated map, so let's look at an illustration. So here we have a sequence represented as an infinite dimensional vector. So the elements of the sequence are x1, x2, x3, x4, and so on up to infinity. And now we map this sequence by the left shift operator sigma 2, for example. And then what we get is another sequence that starts with the n plus first element, so in this case the third element. So the sequence here is x3, x4, x5, and so on. As you can easily check, if we put the sum of two sequences into the left shift operator, the output will be the sum of the two shifted sequences. Moreover, if we multiply this sequence by a scalar alpha, what we get is the alpha multiple of the shifted sequence. So therefore, the left shift operator sigma n is indeed a linear map according to definition 6.1. The third example is the so-called Volterra operator that we denote with a capital V, and it maps from the space of continuous functions, for instance on the interval 0, 1, to the space of continuous functions on the intervals 0, 1. And what it does is it takes a continuous function, for example f of t, and maps it to its primitive function. So the integral from 0 to t of f of tau d tau. Now the question is again, is this a linear map? The answer is yes, V is a linear map. Why? We check the two properties of definition 6.1. So first, if we take the integral of the sum of two functions, it will be the same as the sum of the two integrals. And second, if we take the integral of a scalar multiple of a function, it will be the same as the scalar multiple of the integral, because we can always pull a scalar out of the integral. As a fourth example, we consider the function evaluation map E, which maps from the space of continuous functions on the interval from minus infinity to plus infinity into the complex numbers, and it's defined as E of the function f is simply the value of the function at the point 0. To better understand the meaning of this map, let's also look at a quick illustration. So here we have a continuous function f of x on the interval from minus infinity to plus infinity, and how the map E works now, it takes the entire function f and maps it to its value at x equal to 0. Now the question is this function evaluation map E a linear map? To answer this, let's just go ahead and check the two properties of definition 6.1. So let's take another function g of x and observe that E of f plus g is just f of 0 plus g of 0, which is the same as e of f plus e of g. Moreover, e of alpha times f equals to alpha times f of 0, so it's the same as alpha times e of f. So we conclude that the function evaluation map E is indeed a linear map. As the fifth and final example, we consider the operator R that maps from the space of n by n real matrices into the space of n by n real matrices, and it maps a matrix X to the matrix X transpose AX plus X for some fixed matrix A in Rn by n. Without going into the details here, you can easily check that R is not a linear map unless the matrix A equals to the zero matrix. So what these examples are supposed to do is to give you a vague idea of the generality of definition 6.1 and of the diversity of the sets of linear maps that are out there. Now we move on to the definition of the adjoint of a linear map. To this end, we have Theorem 6.2, which states that if L is a linear map between two Hilbert spaces V and W, then there exists a unique linear map that we call L star, and which maps from W to V, and which satisfies that the inner product of L star Y with X in the vector space V equals to the inner product of Y with Lx in the vector space W, and that holds for all X in V and all Y in W. And this unique linear map, L star, is called the adjoint map, or simply the adjoint of L. We prove Theorem 6.2 in several steps. To start, let the set of vectors bi in V be an orthonormal basis for the vector space V, which exists because every vector space has a basis, and we can always use the Gram-Schmidt procedure to make this basis into an orthonormal basis. First of all, note that any vector x in the vector space V can be written as x equal to the sum over all I, which stands for the sum from I equal 1 to the dimension of V, of the inner products of the basis vectors bi with x times the basis vectors bi. The proof of this fact is actually quite simple. Certainly x can be written as some linear combination of the basis vectors bi. And now all we need to do is that we need to show that each alpha I equals to the inner product of bi with x. Now certainly, if these two vectors are equal, their inner product with any other basis vector bj will also be equal. By linearity of the inner product in the second argument, we can now pull out the sum and the scalars alpha I in front of the inner product. And now we get here the inner product of bj with bi. But since the basis vectors form an orthonormal basis for V, this means that the inner product is 0 if the indices I and j are not equal, and the inner product equals to 1 if the indices I and j are equal. So therefore, this whole expression here simplifies to alpha j. And hence, we have exactly what we wanted to show. By linearity of the given linear operator L, we therefore clearly have that Lx equals to the sum over all I of the inner products bi with x times L bi. Next, we're going to prove the following fact. Let y be any vector in the vector space W and consider the map phi that maps from V to the field and which is defined by phi of x equals to the inner product of y with Lx. Then there exists some vector z in V such that this map phi of x can also be represented as the inner product of z with x. For the proof of this fact, suppose we define the vector z by this formula given here. Now all we need to do is for this z to verify that this expression and this expression are the same. So let's start with the inner product of z with x and substitute this expression for z. Now we can use conjugate linearity in the first argument to pull out the sum and these scalars. Note that by conjugate linearity, when we pull out these scalars, we have to take their complex conjugate, and hence the line above these scalars disappears. And now what we can do is, by linearity in the second argument, now of this inner product, we can pull these scalars inside of this inner product, the result of which is this expression, where we now realize that the second argument of this inner product equals exactly to the expression for Lx. And so we get exactly the desired result. So we have just shown that for any given vector y in W, there exists a vector z in V such that the inner product of y with Lx equals to the inner product of z with x for all x in V. Now what we want to show is that this vector z is unique, and hence the map L star that maps from W to V and which assigns to any vector y the unique vector z is well defined. For the proof, suppose there exist two vectors c1 and z2 in V such that the inner product of c1 with x equals to the inner product of z2 with x for all x in V. Now we can bring this term to the left-hand side and then use conjugate linearity in the first argument to obtain that the inner product of c1 minus c2 with x must be 0 for all x in V. In particular, we may pick x equal to c1 minus c2, and then we get the inner product of the vector c1 minus c2 with itself, which of course equals to the induced norm of this vector squared, and this has to be equal to 0, so therefore this vector has to be equal to 0, or in other words, z1 must be equal to z2. Hence, we have proved uniqueness of the vector z and well-definedness of the map L star, and what remains to be shown is that L star is indeed a linear map. And to show that the now well-defined map L star is indeed linear, we can just check the linearity properties, so the additivity and homogeneity of this definition of the vector z. And it's easy to see that they are satisfied, as we can just substitute y1 plus y2 here, then pull these inner products apart, and then also split the sums into two separate sums. And analogously, we can add alpha times y here, then pull this alpha out, which by conjugate linearity has to be the complex conjugate of alpha, but then we have the complex conjugate here, so it becomes alpha again, and hence homogeneity is satisfied. For the special case of our finite dimensional complex vector spaces, we have corollary 6.3, which states that the adjoint map of a matrix A in Cm by n is uniquely given by its adjoint matrix A star in Cn by m. For the proof of corollary 6.3, pick any vectors y in Cm and x in Cn, and note that in the special case of Cm, the inner product of y with ax equals to y star ax. Similarly, in the special case of Cn, the inner product of a star y with x is defined as the vector a star y star times x, which equals to y star a star star x, and a star star x is known to be equal to a. Hence, this also equals to y star ax, and so we have proven that the adjoint matrix A star is exactly the adjoint map that we were looking for. For general adjoint maps on abstract Hilbert spaces, we have a generalization of facts 2.4 and 2.8b in lemma 6.4. Suppose we have three linear maps K, L, and M that map between the appropriate Hilbert spaces, then the following properties hold. A, the adjoint of a linear map equals to the linear map itself. B, the adjoint of the sum of two maps equals to the sum of their adjoints. C, the adjoint of the combination of two linear maps equals to the combination of their adjoints, where we now have to invert the order of the combination. D, the adjoint of a scalar multiple of a linear map equals to the complex conjugate of the scalar times the adjoint of the linear map. And E, if L is invertible, then the adjoint of the inverse equals to the inverse of the adjoint. The proofs of all of these statements in this lemma are not very hard, and hence they are left as exercises.